In the last section, we studied orthogonal projections. Here we'll apply them for the Gram-Schmidt process and QR factorization. The Gram-Schmidt process is an algorithm to produce an orthogonal or orthonormal basis for any non-zero subspace of Rn. See this example? W is the span of x1, x2. These two vectors are from R3. We'll try to find an orthogonal basis for W. The main idea of the Gram-Schmidt process is to use orthogonal projections. For given x1 and x2, first we'll project x2 onto x1, and v2 is orthogonal to x1. That is orthogonal projection. Now, rather than x1, x2, we'll try to choose v1 and v2. Of course, v1 is x1, and v2 is, from here we can get it. Now, because v2 is a linear combination of x1, x2, and so that the spanned space of x1 and x2 and spanned space of v1 and v2 must be the same. So that's the idea. And let's try to solve the problem by using this technique. Okay. Now, x2 must be projected onto the space of x1. So here, x2 is alpha x1 plus v2. For this projection, alpha must be x2 dot x1 over x1 dot x1, right? Okay. x2, x1 product is now 3 and plus 12. Now, x1, x1, that is here 9 plus 36. Okay, so it is a 15 and that is 45. So it is a 1/3. Okay, so v2 can be here x2 minus 1/3 of x1. Okay, what is x2? x2 is 1, 2, 2, and minus 1/3, and x1 is 3, 6, 0. Okay, so here that will be 0, and that will be again 0 and 2. Okay, so here if we collect v1 and v2, then that's the space, orthogonal basis. Here v1 must be x1. So v1 360, and now we got v2 here, that is 0, 0, 2. These two vectors will form a new basis for W, but now these are orthogonal. So these two will make an orthogonal basis. Okay. See this figure? x1 is here. Now x2 is this vector. Rather than using x1, x2, we try to project x2 to the space of x1, and that is the projection, and this is the orthogonal component, and so that here v1, v2 are orthogonal, and they form an orthogonal basis. Okay. Now we'll generalize that idea, and that is the Gram-Schmidt process. Given a basis, that means they are linearly independent for a non-zero subspace W of Rn. We define in this way. From x1, just we define v1. Now x2 is projected to v1, in fact x1, v1, and remainder part is v2. So after projection, we try to get v2. That is orthogonal component. Because they are linearly independent, always we have that non-zero orthogonal component. Now we'll go the next step. Now x3 is projected into the direction of v1 and also onto the subspace of v2, and remainder part is an orthogonal component v3. So after projection, we rearrange in this way. v3 is obtained from the orthogonal component. Again, v3 is non-zero because they are linearly independent. Keep going, and we get such formula. Then v1 to vp, the set of these vectors is an orthogonal basis for w. In addition, now if we consider the subspace spanned by k vectors, this is first k vectors of x, and that is first k vectors of v, but these two spanned space must be the same. The span of x1, x2 and span of v1, v2 must be the same because they are really linear combinations of earlier vectors only. And of course here, the span of x1, x2, x3, these three vectors must be the same as the span of these three vectors. Is we are taking orthogonal components, however, they are all linear combinations of these earlier vectors. Okay, so that for each k between 1 and p, the spanned subspaces are the same from x and from v. Okay. This is orthogonal basis. Now, once we normalize the orthogonal vectors, then this orthogonal basis becomes an orthonormal basis. It's normalized, that's it, so that it becomes an orthonormal basis for W. In reality, the Gram-Schmidt process is often implemented with a normalized Gram-Schmidt process. That means that this normalization is included in the algorithm. Okay, let's try to find orthonormal basis for W. That is the span of x1, x2, x3, and these vectors are given. They are all from R4. Okay, let's do that. By using the Gram-Schmidt process, we here start with V2. V2 is the same as now x2 minus alpha x1, right? And alpha can be found here. That is, x2 is projected into the space of x1, so that x1 dot x1 on the bottom. Okay, now this dot product is minus to 0, minus 3. Okay, so it's a minus 3. and x1 dot x1 1 1 1, that is a 3. So that is minus 1, which means that this is the same as, okay, now alpha is minus 1, so we have to add two vectors, x1, x2. Addition is minus 1, addition is 2, addition is 0, and 1. Right? So we got V2. Now V3, okay, that is, first we can project, let's try to start with x3. x3 must be projected to now alpha 1 and V1. Of course, x1 is V1 and plus alpha 2 V2, and then here V3. We have to get that one. Now, for this orthogonal projection, alpha 1 must be, now x3 is projected onto the space of V1, so that must be x3 dot V1 over V1 dot V1. Now V1 is x1, so the x3 V1 dot product 0 0 1 1, so that must be 2. Okay, V1 dot V1 we already know that is 3. Okay, now it's not integer, but anyway. Now alpha 2, that must be here x3 is projected to V2 and V2 dot V2. Now x3, that is V2, dot product must be 0 0, okay, that is 0, and 2 0 and plus 1, so it is a 3, and V2 dot V2 1 4 1, that is a 6, so that is a half. Okay, so we have to do non-integer computation, but anyway, so V3 is same as x3, which is here 0 1 minus 1 and 1. Alpha 2 is 2 over 3, and V2 just the one, alpha 1, okay, that one, and V1 is x1. There's 1 0 minus 1 and 1, and alpha 2 is 1/3. No, that is half, right? Half, and that must be half, and V2, that is minus 1 2 0 1. Okay, you can simplify yourself, and then after that, that is V1, so you have to normalize if you want to get orthonormal basis. Then there's V1 and U1 can be gotten. The length is square root of 3, so that divided by square root of 3 will be U1, and that is the length is square root of 6, so the V2 divided by square root of 6 will be U2, and after getting this one, again, divided by its length, then that will be the final vector U3. So U1, U2, U3 will form a new orthonormal basis. Okay. Now we can use the technique for QR factorization. A is on n by n matrix with linearly independent columns. Then A can be factored as QR, where Q is on n by n matrix whose columns are orthonormal, which means that Q transpose Q is identity. Now R is on n by n upper triangular invertible matrix with positive entries on its diagonal. We can make this factorization. The proof of theorem is quite simple. The first step is, now we start with the metric A, and the columns are linearly independent. So we can get orthonormal bases and orthonormal columns for the column space of A. The W is the column space of A, and these are original columns of A. Now from there, we can get orthonormal bases. Now we define the collection of these vectors as Q, and now this is a basis. So for each xk, now each the columns of A, now we can make projection. Then we can get such expression for each xk. Now we try to collect this coefficient, then that will be R. So that's it. The major idea is like that. So we can get QR factorization. Let's see here the algorithm for QR factorization. Now A is a metric having x1 to xn, and assume these are linearly independent. Then first we apply Schmidt process to obtain orthonormal basis for the column space of A. Now we try to make here expression. So x1 is projected in U1, and x2 to U1 and U2 subspace, and so on. Then here the Q is collection of the orthonormal bases, and now R is the collection of the coefficients. Or once you got that here Q, then you may try to apply Q transpose to A, then you can get R. Now the thing is, the diagonal must be positive. Okay, here we can do in this way. And here RKK in QR factorization R, this is on diagonal entry. That is positive. If it is negative, then we multiply -1. For example, if this is negative, then we multiply here -1 and also -1, so that this original orthonormal basis will be changed during the computation. If this is a minus, then we multiply both -1, so that eventually it becomes positive. And again, even though you multiply -1, the orthonormality is not changed. Okay. Okay, here. In practice, the coefficients Rij, which is ui.uj, xj, can be saved during the normalized Schmidt process. Okay. In practice, it is implemented in this way. Now, let's try to find the QR factorization for A given in this way. We'll follow this algorithm. First, we have to use Schmidt process to get orthonormal bases. And then we can get, and of course, the collection of these vectors will be Q, and R can be obtained through that dot product. Okay. Now, x1 is 4 and 3, and x2, the second column, is minus 1 and 2. We'll try to project x2 onto the space of x1. So there's alpha x1 plus v2, right? Where alpha must be x2 dot x1 divided by x1 dot x1. Okay. x2, x1, dot product minus 4 plus 6, which is 2, and divided by x1 dot x1, 16 plus 9, 25. So here v2 is the same as x2, that is now x2. x2 is minus 1 and 2 minus alpha 2 over 25, and that is x1, 4 and 3. This one, okay, that same as 8 over 100. So minus 1 minus and 32 over 100. So that minus 1.32. For this one, okay, 2 minus, and there's 8 times 3 is 24. So that must 1.76, right? Looks like this one is, okay, minus 3 and 4. So that is, let's see in this way. This difference is 0.44, and now minus 3 and 4, like that, right? Okay, so we got here v1, x1 is v1, and v2 is given here. So orthonormal basis must be u1. The length is 5, so the divide of 5, so we can get u1. Divide the 5, then that will be 0.8 and 0.6. Okay, and u2, okay, these are essentially the same. Length is 5, so that is minus 0.6 and 0.8. Okay, we got from here u2. So this will make orthonormal bases, and the collection of them will Q. Okay, Q is here. Now you can get R quite easily, and by using this, the formula you can get it, or just simply you can multiply Q transpose to A, then you can get R. Either way, you can finish the computation. Okay, so you can finish it yourself. Here we have alternative calculations of least squares solutions. A is an m by n metric, and we assume m is larger than or equal to n, and also assume rank of A is n, which means that the columns of A are linearly independent. Then we already know that the least square problem and AX equals B has unique solution. And the unique solution, and here we can solve by using the least squares, the method of normal equations. We multiply A transpose in front of from left hand side for given equation, and we try to make inverse so we can get it. So the metric A transpose A inverse and A transpose, that portion looks like inverse. From here, X is now, we don't have A inverse once M is larger than N, but that is playing the role of inverse. So we call this portion the pseudo inverse of A, and we are trying to use the notation A plus. We did this one earlier. Now, here we'll try to solve the problem, least squares problem, by using QR factorization. The same A metric A, n by n metric, and with linearly independent columns, and A equals QR is on QR factorization of A. Then for each choice of B from Rm, the equation Ax equals B has a unique least square solution given by R inverse, Q transpose, and B. Okay. For a proof of the theorem, we try to get the pseudo inverse. Okay, A is QR, and the pseudo inverse of A is here. Now, that is A is QR, so QR transpose, and QR, that inverse, and A is QR transpose. So by using simple algebra, we can reach at that is R inverse Q transpose. So basically this term is the same as now that one, so that we can get the unique least squares solution, right? For this problem, now we try to get the least squares solution of Ax equals B. Now A is given here, B is given here. We can easily see that the columns of A are linearly independent, so that we can get QR factorization with a diagonal positive. And once you try to get the solution, then first you apply transpose of Q and inverse of R. Then you can get it. Try yourself. Okay, that's the end of the section. Thank you.